Well, good morning, everyone. It's a pleasure to be here with all of you. And, the whole purpose, I think, of blockchain is decentralization, and we are all part of the decentralization movement. And it, it may be a winner take all kind of a game ultimately, which whether decentralization or centralization prevails. It will certainly help decentralization to get a lot of users and momentum. And the thing that's historically in information technology brought the largest and fastest uh, adoption of a particular thing app has been messaging and chat, unquestionably, historically over and over again. And that's part of the reason we've been focused at Elixir, and it was now part of X6 Network, on making a distributed, totally decentralized chat system that is uh, attractive to use, and that requires it to be low latency. In other words, there can't be too long a delay between when you send the message and when it's received. And I open sourced CMix, mixing in general. I'm sorry, back 40 years ago, and there have been a whole series of implementations of it, from Mix Minion to Mix Master. There was the work at in Dresden by Andreas Fitzmann, now deceased, unfortunately. There was the Zero Knowledge Network, and then Tor, brought to you by the CIA. Some of these projects, none of them really has done that well technically, in my view, and some of them have, tried to make mixing their own. They didn't want to acknowledge that what they were doing was mixing, but many of them celebrated it. But there's also been 5,000, I read, publications that reference the original mixing article that I wrote back, when I introduced mixing, and nobody has found a way to speed it up. In other words, to reduce the delay between when you send a message and when it's received, until the CMix team found a way to reduce that by a factor of 1,000, roughly, maybe a little more, by allowing all the computation to be done in advance and reducing the amount of computation that has to be done in real time. And this is a fundamental improvement. And by using the very large batches and choosing the teams randomly, we've created, in a distributed manner, unprecedented level of security. Now, you may think, well, this is all, maybe that's over much than is needed, but I don't think so. So first thing is, we need to really create a messaging system so that we can get widespread adoption to get decentralization to take off. I think that's clear. Do we need a fully decentralized system with low latency? Yes. Centralized messaging systems that people have migrated to because of privacy concerns have two fundamental problems. One is that those who operate the system, whether it's Apple or whoever, can see all the message traffic. In other words, they see who's talking to whom and when. And they also often are involved in the setup of the keying, so they see who has established communication with whom. And moreover, and you don't have to take my word for it, but there are some articles in the literature which have carefully analyzed the protocols for even the Apple Messenger, showing that they technically would have the ability to what's called man in the middle the communication. That means they could intercept the setup of keys in such a way that they can create a key for themselves and sort of play one side off against the other and listen in on all traffic for that pair of communicants and change the messages at will. And so these are very fundamental problems. So I think that what we've done here at Elixir is just a huge breakthrough from a technological point of view, finding a way to fully decentralize mixing, implementing this super low latency approach in a really surprising and great way by randomly choosing the teams and everything, and also just the whole community support of having several hundred, 260, I think, about individual people who have built high-powered special computers to run this CMix, and we've been running in beta, as you know, for quite some time now. So, I mean, in the whole history of mixing, there hasn't been this kind of a grassroots, powerful network built at all. So this is a huge thing in and of itself, and I think all of the members of this community are to be congratulated for their participation in this. So, I think tying it all together, what we as a and I'm not speaking very broadly, as the community and internally in the Elixir project itself have done is an amazing thing that really has a good chance of tipping the balance towards decentralization by allowing a rapid growth in messaging of a fully decentralized system. So it's with the metadata shredding, this is so this may be the beginning of the win for decentralization, and all of the participation and help that's brought us to this point is so much is appreciated and will be appreciated in the future, I think. And so at this call, we're going to be talking about opening up the endpoint interfaces, and that's, of course, brings up a whole another level of the possibility to make dApps that use the CMix messaging system. And there's a lot of interesting stuff that can be done. And having this building block available for dApps on the XX network is going to allow a lot of unique, special kinds of dApps. And we've got about half a dozen we've been working with that we're really excited about that really wouldn't be able to operate without this kind of infrastructure. So without further ado, I'd like to turn over to the members of our team who are up early here and in this call, and some of whom you may not have. So I think everyone knows Ben, who's put this, done a lot of work putting this whole team together, putting the network together, and also Rick. I'd like just to say a couple words about Rick and I have worked together since maybe 2008. We ran and Rick did most of the IT work on that. The central part of it, the public elections in Tacoma Park, Maryland, 2009 and 2011, in a publicly verifiable way. It's the first time ever done. So that work is now being followed on by the VoteXX project, which is one of the dApps that I was mentioning that uses the CMix, and watch for that. You can see it at votex.org. You can read a little bit about it. Rick's quite an amazing guy. He's done a lot of different things, and a lot of different people have appreciated his superpowers. But now he's back with us working on this, so it's fantastic. And also, I should say, I've actually worked with Kate on and off for it's probably 6 or 8 years. I don't want to, when Kate first started as an intern with us years ago on a different project, and I was blown away by how clearly she was able to think things through, and her ability to just move things forward in a really excellent way. So I think we're super lucky to have her as as someone behind the scenes, but as a part of pulling an awful lot of the user side of all this together in a great way. So I guess I think I'd like to turn the meeting over to Ben, who will take you through it, and I will look forward to meeting with the rest of you in the future and staying in touch. Okay, thank you again for all your support.
Thank you, David. That was a wonderful intro. We have, so we're going to present on the XXDK. This is software that we've been working on for a while now. And it's kind of a key thing missing from the beta net, because as currently we're testing dummy messages, and this will move us to real communications. What we're going to see here is kind of the bedrock of both what we are, what you need to use it now, and the bedrock for the rest of the features that the XX network will eventually have. So we're going to start talking about the general feature list of what is available. We're then going to go into functionality and concepts. There's some ideas here about what we're doing, which are currently which you might not be aware of. We're then going to talk about the command line. You can actually use this API right now to send messages. It's not the prettiest mechanism, but you can use it. So we're going to show you how you can do that, and then we're going to do it ourselves using a test network. We're then going to go over some details of the API and then talk about the roadmap. And actually, don't have a bullet here. We're then going to talk about some implementations and use cases for this SDK as it currently stands. So I'll go straight into it. So the feature list of what we've got released right now, which you can find on our the Elixir GitLab, it's now available under BSD license, is network following. And this network following header is probably, we'll get into it, but it's a new concept within this type of system, because normally when you have any type of messenger, there's a server that stores messages, you go to it to send, you go to it to receive. It's fairly simple. Within a decentralized system, that's not the case, because your entry points to these mixed networks are constantly changing. The exit points are constantly changing. Not every server and every node in every network has every message, because that would be the amount of storage each would require would be phenomenal. So you end up with this interesting problem where this client needs to be able to send and receive this mixed network without having anywhere to track. And it's the network following which lets it do that. So it's pinging the network, finding out what it's doing, and then so it can know where to send messages. And through a system, it gets these little probabilistic proofs that tell it where its messages are available. And so the second is network registration. You've got to do a bunch of key exchanges so that your stuff stays secure. That's critical for CMIX. It handles this automatically. You have to do the sending of private and secure messages, which include end-to-end encryption, which is critical here. We've got a custom solution, which I'll talk about a little bit, which is designed specifically to work well with CMIX privacy-preserving technology, which brings its own challenges for end-to-end encryption. And we then have the receiving of messages, which is, as we've discussed, this process of message pickup, and then decrypting it so you can read it. There's other components here that have to be here. They're not the core features, but to be able to use this, you need the ability to handle threads, handle states. You need to pause the client, be able to resume it. It's not the easiest thing to do. And then we've got a secure storage system, which is actually in itself metadata protecting. So the idea here is that it encrypts data before it stores it to disk and encrypts the keys. It encrypts, and it does so in a manner we can't even tell what keys it has. So if someone gets your phone while the app is not open, they can get this encrypted store, but they can't do anything with it, and they still can't tell who you're talking to. So it's meant to preserve the metadata protection from the phone side as well. So I guess we'll get straight into it. So I'm going to talk about some functional features and concepts. And we'll get back to network following. So as I've said, a feature of this client, which exists but is not present in many other similar systems is network following, in that you have this network which is constantly progressing, constantly producing new batches, completing them, and you need to know where to send your messages. You also need to know where to pick it up. You need to know what messages are available. You need to know, for example, new nodes to register with or new events in the network that you have to handle. So it's this. So every gateway creates this curated list of data as to what's going on, and you're able to contact any gateway, and you get these chunks of data. You can read them, and you can understand what to do. It has the ability to handle downtime. So if you've been off for a while, it picks up select data. It doesn't download the entire history of the network for the last month you've been offline. And there are mechanisms in there to do that securely. And it can be suspended and resumed at will. So there needs to be ability for the system to be stopped because, as you can imagine, it takes up some processing power and some bandwidth. So you don't want it running when you don't need it, and then resumed. So all of that is built into the SDK. For message retrieval, this is actually, with regards to network following, one of the hardest problems to solve in a centralized system. Because imagine there's 200 nodes as there currently are. You don't want to every single second have to ping every single node of the network to check every single node if you've got a message on it. That'd be a little bit insane. So it's currently designed to store your messages for 1 week. It doesn't store them forever. We may be able to expand that as time goes on, but the 1 week is for the current storage available. Is designed for the current storage available, making sure that we don't run out of space on the nodes. What happens is that when a team finishes mixing, it gets output, and each output is an end-to-end encrypted message, which then relates to a specific user. It tells you who it's for, but it doesn't tell you where it's from. And that's kind of the point here. It disassociates sender from receiver. And what happens is the gateway uses a gossip to tell the other gateways, hey, I've got messages for this list of people. And then the gateways build these thing called Bloom filters, which is a theoretical thing in computer science, where it's a data structure which lets you know probabilistically if something is in a set. So in other words, let's get less technical. You can check to see if your message is in a Bloom filter, and it will then tell you if it is or not, with some probability of failure. And the failure will always tell you that it is there when it isn't. And it's this compression mechanism, so we can give you these short proofs that let you know where your message is to pick them up while using little bandwidth. So clients pull, they get these Bloom filters, they get some other object called known rounds, and they combine this together to understand where they've got messages available. I think that this system, what we've built, it's really designed for mobile use. So what we end up doing is this system is a privacy to performance trade-off, because you do have to gossip this information. But in the future, we'll have options like pushing specific IP addresses for non-mobile use, and people can set their own mailboxes. I don't think this is the end-all be-all, but it is the kind of basal case that works across the board, so it's what we've implemented. And as the network grows, and as there'll be more options where people can select trade-offs for themselves, and I think that's a very important part of this, where individual users are kind of in control of their own data, they're in control of their own metadata, and they're in control of their own decisions. It's a key idea. Let's talk about a few other concepts. So then we have the idea of authenticated channels, which is, this is end-to-end encryption, and it's the process for creating an end-to-end link. When two users don't know each other, they need the ability to contact each other and create that end-to-end encryption, and we've built a system that runs over CMIX, and it's peer-to-peer. So if I know your information, you know my information, we can contact each other and never touch a centralized server, not once. And that's pretty important, because it means that at the base of the Elixir network is a completely decentralized. You don't have to ask permission to talk to someone. In fact, if you can get the data from someone else out of band, at no point in time does any centralized party know who's talking? So I can come back to answer questions. We've obviously more detailed on this. It's a specific payload where you send keys and you send and there are fingerprints involved, and then you've got that encrypted payload. So, but this is the core key negotiation mechanism for the system. And then that goes into end-to-end encryption. As I've mentioned, we have a specially designed privacy-preserving end-to-end encryption system. When you send a message, you've got an end-to-end encrypted payload and then a non-end-to-end encrypted payload, all wrapped within the CMIX mixed payload. So when it comes out, this tail of the message has who it's designed for and then a fingerprint. And the recipient, through the negotiation system, knows, oh, that fingerprint came from Ben. But no one else does, because no one else was a party in that negotiation. So it's a special end-to-end encryption scheme designed to give you an understanding of who's talking to, designed to let the receiver see who sent the message without the network itself knowing. Obviously, these are negotiated through authenticated channels, and it's designed to auto-renegotiate when it's out of keys, but it's designed in a mechanism where one side can push a negotiation so that one side can continue sending messages forever without waiting for interaction from the other side, which is an important thing in these kinds of systems, because ultimately you want it to be as flexible as possible. And then we've got user discovery, which is a centralized system. It's in progress, but it utilizes CMIX to have very robust trustless features. So this is a system for contact pickup and verification. This is over the network and the ability to figure out, to find someone else to talk to. There is a problem where the piece of information we know about each other already are connected to centralized systems. So for example, it's impossible for the system to verify an email without sending the email, and you can't send an email without knowing the email address. So the system itself has you initially register your actual email or actual phone number so that it can verify it. And I hope we can find a way to get around that in the future, but currently that's what we've got implemented. But the important part of user discovery is that a user is registered, and then other users can query their information. And when you do that querying, it's done over CMIX through a one-time use identity. And as a result, the user discovery system can't see who is talking to who. It knows that requests were made, but it doesn't know who made those requests. And that's pretty unique to the system. And it's going to be and actually a very hard thing to do. So there are some systems out there that approximate these properties. They use things like Intel SGX or other technologies which are of dubious quality and have had problems. And so this is comparatively very simple to implement. It's close to being done. As you can see with the open source client, you can actually see the progress. It's basically implemented. We're in the testing phase currently. And this is not mandatory. I don't know where in the system do require use a centralized system, but it is available to make it easier to find other users. So that's it's an important feature. And then I want to talk a little bit about rate and account limiting. This is kind of a side topic, but it's going to be important, which is that currently we're limiting the number of new users that can onboard, and that's just so that they won't be there forever. I think that once we get to mainnet, using the coins, we're going to have systems to do this. But essentially, we're worried about DDoS attacks with people just slurping up too many accounts. And then there's message limiting, just to make sure no one DDoSes the network. It's not been defined. I'm not sure exactly where it'll be yet, but it's going to be fairly reasonable. It's done through a gateway gossip about who sent messages in each round. Obviously, this is fairly problematic because you can see who sent and who received. That's an issue. We've got mechanisms to obfuscate this through random delays because it doesn't need to be immediate, unlike the message reception component. So this is something which very soon we're going to have more work on, which will further privatize that system. So I'm going to hand over to Rick. We're going to talk a little about the command line interface so you can see what it would be like right now to send a message. Obviously, this is more of an engineering exercise. We use this for our integration tests, and so that we can test it outside of UIs. And so while functional, this obviously won't be how the network will be used, which we'll talk about at the end.
All right, thanks, Ben. So the network is entirely based off of this, what we call the NDF, the network definition file. Contains all of the initial data that you need to connect to the network, which includes the public key of the permissioning server and information for connecting to at least one node. And it also includes like group parameters for end-to-end and CMIX encryption. It's a JSON file. Let's talk about the connection lifecycle. So as Ben talked about, you can discover users through the user discovery, but we really prefer the out of band because we're trying to go out of our way to make it so that we don't know who's talking on the system, much less what is being said. So it's going to be an interesting world in that we don't necessarily know even who is using it versus what is trending, right? So it's a very different world than what we live in right now. That is represented as a contact object, which can be encoded in like a QR code, or in our case, we use JSON files. The general setup is you request an authenticated channel to the partner that you have the JSON code for, or the contact code for, and then you establish that E2E relationship, and then you can start sending messages to each other. So the contact file, again, we're using JSON right now. It's pretty easy to encode this to any kind of QR code or an NFC, near field communication where you tap your phones together or something like that. It's the minimum amount of information necessary to create an end-to-end link. There's options for proving your ownership, and there's options for saying this user owns this email, this user owns this phone number, things like that. Yeah, it's got one public key inside of it, and it's got a byte array of an ID for the user so that you can address them on the CMIX network. So to send a message, you use this using the command line tool. As Ben said, it's extremely unwieldy. That's kind of by design. We're not expecting people to be using a command line tool to be actually sending messages and using it for day-to-day operations. It's more for an integration test. You can send a password for the secure storage. You give it the NDF file. You give it a log file. You give it a directory for the session, and then you give it a destination for who to send to. And again, we're using the user contact JSON files, and then you can send a message. And then the second line here is just showing the user 2 version of that, sending back to user 1. To generate your ID, you have to run it once. Sending the message to yourself is optional, but it's generally speaking, I think it's a good idea just to make sure the network is working. So by default, this will create a user contact.json file, and it will send an unencrypted message. And what that means is when it gets through CMIX, it's unencrypted. The sender is not known, but the receiver and what is said is known. Next slide. So sending unsafe messages, all we did here is, user 1 is now using the user 2 contact JSON to send the message, and user 2 is using the user 1 contact JSON to send the message. And we've kind of highlighted that to make it a little easier to understand what's going on. And to create authenticated channels, this is the world that we want to live in. And what I mean by that is there's a bunch of stuff that happens under the hood where channel creation is somewhat automatic. In an ideal world, both sides would get prompted. You'd both have to say yes. What we've done instead is created in the command line interface only an auto acceptor set of code path, and that's what the unsafe channel creation is doing. So what this does is it runs two clients at the same time. They both establish a connection to each other, and then they send messages to each other. Next slide. And this is the longer form version of what I just talked about. So to start, you send an authenticated channel request. This prompts you and says, "Are you sure you really want to make an authenticated channel with user 2?" On the second command there, we've sent the message. You have to run these in sequence, and it says, "Yes, I accept the channel specifically from user 1." You have to give it a contact information to accept the channel. If you don't do that, a log message will appear that says, "Hey, you received this request from this user. Please rerun it to accept the request." And here's how you sort of complete the process. You send the message from user 2 to user 1. Then from user 1 to user 2. And then user 2 sends a message back, and user 1 receives it. And because it tries to receive one message by default, we have that receive count set to 0 on the first one, and then set to 1 on the last one, just to kind of show you that it's sort of a back and forth type process that happens in sequence on the network. And we have a little bit of a demo. We don't have another slide, do we? Can you check for me, Will? Yeah, so we have a little bit of a demo, which I will show you right now, which is using a lot of these concepts. Share now. And on the right-hand side here, I'm going to be watching log files. And on the left-hand side here, I'm going to be running an integration script that we created, which is going to show you all the commands it's running after it sets up a network on my own laptop. This is quite slow because it's running on a single laptop and it's running 5 servers. So it's going to take it about 10 to 30 seconds to start running rounds. And then it'll create a user, then it'll create a channel with another user using the unsafe channel creation. And then the users will start sending end-to-end messages to each other. And there are still bugs in this, so it may or may not we may or may not see those bugs. So let's see what happens. So I've just sent a message to myself. You can see right here, this is the command line I ran. And now I am going to create a channel request to the RIC42 contact JSON I created. It takes a minute because it's got to generate keys every time. You can see it's adding an authenticated channel for RIC42. And that typically takes a little bit of time to time out. And now we are going to start. We received the channel request, and we're creating a channel for Ben43, and we're starting to send these encrypted messages. And we're going to send 5 each across 2 runs of the network. Oh, sorry, across 2 runs of the clients. And they'll start running the second batch in a minute. It takes it a second to shut down the networking on the client side. We're working on that. And we're done. And in case you're worried that we are potentially lying to you, I will go ahead and show you the server. Of course, it's killing them right now, but if you are a server operator, this is going to look super familiar to you. And I'm going to rerun just so you can see that, in fact, it does do what we say. And This is 5 servers running at once, but you can see rounds being run. And of course, because it's an integration test, we're running from a clean slate with round ID 1. And then it's going to start round ID 2 and 3 and 4 and 5. And that's all I have for you.
Thanks, Rick. It's always amazing just to see these things go, because it's 30, 40 seconds of thousands of hours of work to get this all working. So we're right now running this in a local environment. I'm hoping it's going to take us a few weeks before the network is updated to support these clients. I think we've got a little bit of testing left to do before we're ready to push it. But I'm hoping starting next week, maybe the week after, if we run into a hiccup, we're going to have a test network that we're running, which is publicly available, which will allow you to test this. We want to get into your hands in some form as soon as possible. So there'll be more on that. Now we'll talk a little bit about the API for people who might want to start building something with this or just checking it out. So when you start, you've got to log into a client. When you log in, we'll talk about it a little bit later, but you have to pass it storage. And a new user is, if you need a new user, you call new client, then you call login. Then you have to do what's called register callbacks. So there's various things which I'll discuss where you want to get notified of events. You have to register those events. And then you call start network follower, which starts all the various background processes to handle the network. Not much complexity there. I think we'll let Rick talk about storage, because it's a unique solution.
Yeah, so this is a fairly common type of object in software development, but it's usually not encrypted in this way. And we call it the encrypted key value store. And it is a key value store where there's no central location for the list of keys. So you kind of have to both know the password for the encryption and the value of the key to even get access to the actual data that's being stored inside of each key. All that we require is a directory where you can read, write, create files, which I think is a pretty good requirement that almost every platform can support. We've tested it on iOS and Android and FreeBSD and Solaris and Linux and Windows. So it tends to work everywhere we've tried it. And it's designed to be metadata protecting within reasonable limitations. They're listed inside the README right now. The key and the contents behind the key are protected on disk. And we use this sort of best effort approach to store and flush the changes to disk. And that means that we call the operating system flush command when it's available, and we call a flush command on the directory as well to make sure those changes get written. We store 2 copies of it and then switch to the one that has just been written once it's done. So just pick the newest one every time to make sure that the changes are somewhat atomic and that they, if you get a return from the library, that you can be pretty sure that it's been written to disk successfully. And then we also provide thread safety inside of the same EKV instance. So as long as you're not opening up the same directory with 2 different instantiations of the EKV, you're relatively safe when you're writing to the same key or reading from the same key. It's important to note that it's not a secure memory enclave, so it's not protecting data when it's in RAM. So if you are using EKV in an app and you haven't shut the app down, you might be in trouble in terms of tools that read directly from memory. We're looking into how we can potentially protect the data using a secure memory enclave under the hood, but we haven't gotten there yet. And the only thing that we require from a cryptographic operations standpoint that you provide us is a secure random number generator. We provide one in the other crypto Elixir library. I think it's called FastRNG.
Yeah,
but you can use dev-urandom or pick your poison. The big problem with most random number generators is they're not going to be fast enough to keep up. So we had to sort of create our own solution to make that work.
I want to point out it's not a new random generator from scratch. It uses something called a Fortuna construction to expand randomness from another random number generator. So you pass in dev random to the fast RNG, and then it gives you more bits of randomness than you passed in. So we then have a few things. There's the health tracker, which basically tracks from your perspective the health of the network. Are you seeing the rounds? Are you able to communicate with it? And it's an interface which you can either use Go channels or just function callbacks, and it will tell you whenever that status changes. But it's a utility. We use it internally to make sure when we send that we're sending to a valid network. But it's just another important utility. We also provide the round events interface, which when we get to sending, you'll see for it, but it basically allows you to say, I want to know when this round has this event occur. So without constantly polling, it's again, it's an event model. So you're able to say, for example, if you sent a message in round 8 million, you're able to say, hey, tell me when either round 8 million succeeds or fails, so then I can, on my UI, tell the user the message succeeded or failed to send. I'm sure that there are more uses for this. We found a few others within our code base, but this is just another one of these event models which makes writing against the network a lot easier. And then we want to talk about transmission. There are 3 calls. You have send E2E, send unsafe, and send CMIX. Send E2E, you pass it a message which says where it's going, the contents. And then you pass parameters which says, for example, how many times it retries, what's the timeouts. And then it will return to you the list of rounds that message was sent in, a message ID, which this message ID is commingled with the end-to-end encryption system and is promised to, under the birthday paradox, be unique, and it will, and the same on both sender and receiver. And it'll turn you an error if it occurred. This supports multi-part messages. So if you send a message bigger than packet in that CMIX can handle, it will automatically chunk it out and send it in multiple messages, even across multiple rounds if necessary. Although there's maximum size here, and if you want to send large amounts of data, the logic needs to be a little bit more intelligent than what's in here. Then if send unsafe, which is very similar to send E2E, but does not do end-to-end encryption. This actually breaks metadata protection because on the output, it has to say who it was sent from. This is not, this primarily exists for testing, and we're not expecting users to use send unsafe beyond maybe debugging. And then there's send CMIX, which is a low-level function which sends a raw CMIX packet. You can see it uses a format.message instead of a message.send. This sends a single message in a single round. We're using it, for example, in authenticated channels or in a few other places to build other communication protocols on top of CMIX that don't use the built-in end-to-end encryption, and I think that's its primary use case. So we're exposing an interface to allow bypassing our end-to-end cryptography to implementing your own if you would like to. And then for reception, we have a system called listeners. You register a listener, which can either wait for messages from another specific user or with a specific message type. And it can either be a function, it can be a channel. We've got a more generalized interface if you want to do something different, although I don't know what that is, or could be. And you generally want to register before you start all of these things before you start the network follower so that you don't miss anything. I don't think there's anything particularly revolutionary about any of these systems other than we've provided them to make it easier to build systems with the client. And the last thing is the lifecycle. So running these threads use bandwidth, it uses a CPU, and if the user isn't actively engaged, you don't really want to be running these systems in the background. So we have the ability to start and stop them when you don't need message pickup. And just start network follower and stop network follower, and it's all inclusive. It stops all the threads. We actually have a system that we're working on which allows you to attach your own processes to this if you want them to be directly associated. But that's pretty much it. Start and stop. Implementation, the API is simple.
Yeah, I'd add that the core of the dApps is really on the start and stopping of the network followers. Because what you're going to want to do is you're going to want to create your own network listener, and you're going to create your own process handling for what you do inside of that dApp if you're building for the network.
The other thing we've implemented is bindings for iOS and Android via Go Mobile. This is in the bindings package, and there's instructions in the project README on how to use them. We're using it for the XX Messenger. It's actively maintained. The API is slightly different, but it's only in minor details than the Go one, just because there's, for example, you can't use channels. There's limitations on data types. Overall, it's essentially the same API. With differences are primarily cosmetic. And then I want to talk about the roadmap for this client, because obviously it's not done. We have still some bug fixes left. The garbled and critical messages system, which I'll mention quickly. The garbled is due to the ordering of messages. It's possible to receive a message before you know the keys for it, so this stores and lets you reuse them. It currently has some bugs. And then critical messages is a system which will ensure that messages which have to be sent are sent. For example, rekey messages. So if they fail, it will store them and resend them the next time the network connects. We currently have a bug in the system called known rounds, which are these buffers that describe what rounds I've not checked if I have messages in yet or not. And then there's various uncommon crashes and errors that we will be working through. It's generally stable. Our integration test passes 9 times out of 10, but errors do happen. We're working on ephemeral IDs, which is the ability to create short-term use identities so that you can contact someone without them knowing who you are. This is required for user discovery. It's in progress, and then user discovery itself is in progress. It's close to done. We obviously want to deploy these various things to the network. We're hoping to do that early to mid-January. We want to bring back in the notification system from AlphaNet. This is a centralized notification system where notifications are sent through Firebase. It's optional, and it's relatively metadata secure, and that doesn't contain contents of messages, and when it sends pings is not one-to-one with when messages are received. As I mentioned before, the rate limiting system currently the rate limiting system is currently a little bit too specific as to which user sent in which batch. We can expand that so it still functions as a functional rate limit to ensure the network can't be DDoS, but you don't know which batch it's in over hundreds or thousands of batches. We could increase the round tolerance, which is the tolerance we plan on it, which is how tolerant it is and how good it is at tracking the network, figuring out which rounds are there. There's still a little bit of wonkiness there. The Bloom filter handling, we've got some plans on how to improve it to make it take up less space on the gateways and be able to give you more accurate information as to where you've got messages. We also have plans for gateway mesh networking. One limitation of the current implementation is that you have to contact each gateway directly, and that's not always possible on the internet. You can't always contact all the internet. So the idea that you can route your messages to one gateway from another gateway, that's going to be very important for reliability. And then we want rate limiting also on the IP level so that certain IP addresses can't flood the network even if you've got multiple accounts. That's pretty much the current immediate plans. Obviously, there's more that's going to be built on it. So Praxis will be using this to send messages. There'll be layers on top of it, but those are layers above it, not inside of it, if that makes sense. So it's not the topic of this slide. And I'm going to hand off to, I believe, Kate to talk about XX Messenger. We have we're working on it, and I think that using this, we've got more information on it.
So before I get into the new version of the XX Messenger, I do want to pick up on some of what David said initially, which is when we approached this and we were saying what key dApps will we need to drive adoption of XX Network, we kept coming back to the idea that messaging and communication are foundational. You can't have adoption without some form of communication. Existing communication dApps have some of the biggest user bases out of any global dApps or global apps out there. And so it was clear to us that we were going to need this sooner or later. And when you look at it from a privacy angle, it was clear that we need this sooner because there are apps on the market that are end-to-end encrypted, that protect the contents of your messages, but there really is not a good solution out there to protect all of that other data. Who's messaging who is joining a secure app, and when they're joining it, if it happens to coincide with some major global event. This kind of data can reveal a huge amount about a user. And so we wanted to tackle that initially. A lot of you were with us for the XX Messenger Alpha, which started in November of 2019, and that ran for a few months. And we actually got a lot of good feedback from that test that helped with the design of the XXDK and certainly with the design of the XX Messenger app itself. With the new XX Messenger, we have redesigned from the bottom up. So our core goal in this redesign was that the user should not have to worry about privacy from the start of using the app to finish of using the app. It should be faultless. And how we approach this is we prioritized intuitive use. So when the user is using the app, privacy shouldn't be an afterthought. It shouldn't be harder to set up. It shouldn't be a lag from starting to use the app to getting set up, getting all those features going. It should be as part of the normal use flow. And also, it shouldn't be a hindrance. There frequently is a trade-off between privacy and usability, and we really tried to focus on that and prioritize usability without sacrificing those privacy features. Going along with that, I want to touch on the importance of having network-level privacy. Developing this app on the XXDK it's intuitive from the SDK level. Developing an app on, traditional, what we already have on the internet, it is so tempting to not prioritize privacy. One, those features aren't there. Everything is a retrofit, but it's also so much of the sort of status quo, what's currently in the water is, well, you can just slip a little bit and it'll help drive adoption. You can slip a little bit and collect some data on users and it'll help you target them. Or you have to sort of keep up with the Joneses. All the other apps are collecting data on users, so why not do it too? And we've seen this with a lot of privacy apps out there. They start out really private, and then over time, there shifts to be a focus on the bottom line. They get acquired. Whatever happens, there's some changes, and soon enough, it's no longer the private app it started out as. With the XXDK, that just isn't an option. When you have that privacy at the network level, you can't sort of slip down the road and say, oh, we want to add in all these tracking features. It's just not an option. So having this privacy at the network level not only made it intuitive for us to design this app, but it helps to create better privacy apps as an ecosystem. It's easier to start out with that functionality, and it does sort of create a culture. It puts it in the water that this is the status quo. This needs to be the baseline for everything out there. I did include a little teaser screenshot. We haven't released that much of the UI. We probably will be in the next couple of weeks. But this is just one of the main screens in the app. I'll talk more later when we release more of the UI about sort of the different features, but in the XXDK, they have exposed a huge amount of functionality to us to use. So part of the struggle here is how to take all that functionality, all the different ways you can share information, restrict information, share with other users, connect with users over the network, or connect in that sort of ultra private off network mode, how to take all of that and put it into one nice streamlined user flow. So more of that will be coming over the next few weeks, but this is the new core screen of the app, which is the chat screen. And then I think I'll turn it over to Will, who's going to cover some other dApps that are under development.
Thanks, Kate. So yeah, obviously the XX Messenger is it's been kind of at the forefront of our dApp ecosystem for a while. It it is the dApp. I think that the only dApp that we're currently developing that's completely in-house, but it is not the only dApp we are developing. And so I think there was a question about this in the last webinar, which is, what type of dApp functionality are you going to have, or how are you going to roll these dApps out? And so I just wanted to talk briefly about, what our approach to dApps is and how it's going to evolve in the near future. So I like to think of our dApp approach as kind of three-pronged, where the first prong is sponsoring kind of exemplary projects. So these are projects like the XX Messenger that Kate just introduced. David talked about some of these other projects in his intro to the last webinar, the VoteXX project, XXMPC, and Evidently Online. These are all projects that are leveraging, experts from around the world to make the projects a reality and to really help them solve real world use cases. And so that's why we kind of consider this particular prong to be particularly important. It's because we, as Kate said, we are revealing a lot of kind of unique and unprecedented functionality with these developer kits. And so we think it's important to kind of like give people examples of the new types of problems that can be solved using these tools. So one actually, before I move on, one particularly important in my personal life aspect of this is privacy, because like for the entire time I've worked on this project, it's been a struggle to kind of describe to my parents why privacy is important, or to the general public. A lot of people just don't really get it. They usually think it's nefarious when you talk about privacy. Like, what are you trying to hide? And I think what these projects all do is show why privacy is important in solving problems that are not nefarious. In fact, they're quite fundamental to the way that we live our lives. And I'll go into that in a bit when I actually talk about the three projects we have on the screen. We also have more projects at various stages of development, but we're not ready to really talk about them yet. So the second pronged approach is kind of this build it and they will come approach, which a lot of projects or protocols out there, decentralized networks use, like EOS, where we release a toolkit and we just see what people can build with it. And there's a lot to this approach because there's only so much that we as a team can dream up when it comes to these tools. So like where you're going to see the most innovation, I think, is when we release the tools to the public. They've seen how we've built some interesting things with them, and then they're just going to go out and dream new ways to, or solve new problems with these tools that we never even considered. So this is an important aspect, which is kind of what we've kickstarted in this webinar with the initial release of the XXDK, where we just give you some tools and see what you can do with them, and that'll help us inform the way that we develop the interfaces to those tools and make them more mature as the project evolves. The third fork is extensible interfaces, and I don't want to go too in depth on this other than to say, with these projects, it's important, especially decentralized projects, because at some point we give the reins over to you, the community. And so we want to make sure that at that point, there's a system in place for these tools to keep growing to meet the needs of developers and community members. And so that's the third prong approach, which is making generalized extensible interfaces so that these tools can grow as people dream up new needs. So now we're going to dig into the three dApps that are kind of shown here. The first is the VoteXX project. This one's very exciting because it's particularly applicable to a lot of people, here in the United States who have lived through this most recent election and have really come to terms with a lot of the distrust that's out there with the way that democratic elections are run. And so this project really enables a future in which citizens, as it says, can vote on their smartphones securely and privately, but also it allows people to, well, it allows the elections to be more trustworthy from a societal standpoint, in that users are able to verify their votes themselves securely and privately. You can accurately tally and mark ballots, and it allows for a much more streamlined user or yeah, I guess I would say user interface or user experience in voting, because going out to a polling place can be a real struggle for a lot of people, especially now that we're in a pandemic. So the VoteXX project currently has a lot of academic experts from around the world taking part in it. David's got a huge role in this project as well as our cryptographer Mario, and Rick as well, who did a lot of this work during his PhD thesis. So this project's coming along really well. We're really excited about it. And this project, as well as the next project, which I'll get into, are really interesting as dApps because they're a bit recursive in that, while they can be projects in and of themselves that are usable to the general community, they actually also are tools in and of themselves, in which you can build like a next layer on top of, which I'll get into with Evidently Online. So the next one is XXMPC. So this is a new multi-party computation protocol, which really allows us to build new types of smart contracts. This is something David touched on in the last webinar, and I think is really exciting because for the first time, it looks like we're going to be able to allow a decentralized network of nodes to compute complex operations on private data without having to trust a single node or entity with that data. So I think one of the examples David used was like just signing a signature over a set of nodes. In order to do that traditionally, you would have to trust those nodes with the private key of that signature. So what we're hoping is that this really allows us to build some really cool smart contract functionality that simply isn't available in any other network. So let's get to Evidently Online. So this one is probably my favorite on this list because and I'm a little biased because I've been intimately involved with David as well in our spare time, late nights, trying to touch base with some other experts in the field to make this happen. But I think it's exciting because it really brings together a lot of the unique capabilities of the XX network into a product that is immediately useful and immediately recognizable to mainstream users. So this is a stealth project, and really at its core, it's trying to battle the fake news problem that we've seen kind of come to a head this year. And it does that by incentivizing users to go out and identify and tag fake news as they see it, and it'll have like its own coin and reputation system, which will be used to award jurors and also people who find and tag the fake news. It utilizes VoteXX in these juries so that they can securely and privately adjudicate whether or not certain articles or social media posts are fake news based on evidence that is privately submitted by users using the privacy of CMIX and Elixir. And yeah, I think this is going to be we're going to release more information on this soon, but I'm just really excited about this particular dApp. We do have a couple more dApps that, as I said, we're not quite ready to revealed to the public, but in the next few weeks, I'm sure we're going to release a lot more information, not only about these dApps, but more dApps as they come out. So I think that's it for the dApps.
I think that is the total of what we have prepared to present. I think we had a few questions, so we'll spend a few minutes quickly looking over them and come back and answer them, and any more that you have, those watching. So just stay tuned for a minute.
Well, this has been a fabulous webinar. I mean, it's extraordinarily impressive to see the level of detail and thoughtfulness in all the developments, the perspective that the various team members are sharing and have brought to their work to inspire the whole group. And we couldn't have done any of this without all of the support from the community and the ideas, the interest, and all the concrete things that have been done, and the continual following. And now, we're putting things a little bit in your hands to help us figure out how to get this going and to take the lead on various new kinds of dApps that are enabled, and to help move this all forward. So we're welcome to all of you to a little more engagement and working together to make all this really happen. When you're trying to get everything, all the technical details worked out, it's kind of a heads down, somewhat of a stealthy atmosphere is best. But I think that what's emerged has, not to diminish the help from the community, but is really spectacular. And so I want to just congratulate everyone here. These are just team leads. I mean, we have a whole team behind them, and their work is, of course, also an important part of this, and all the input we've gotten from the community at all kinds of levels. So thanks to everyone, and let's now take it from here.
Thank you, David. So we've got a few questions we've been asked. I'll take the first two. Ethan Connolly asked, what kinds of data are included in the metadata tag? So in our mind, metadata is who you're talking to, when you're talking to them, how much you're saying. And that's basically what CMIX currently obfuscates. This leads into the second question here, which is, again from Ethan Connolly, surely over time a machine learning model will work out what to look for. And that's certainly true. One of the weaknesses of mixing in its most basic implementation is that you can start correlating stuff over large periods of time. If you go look at the initial CMIX academic paper, they've got a solution for this called dummy messages. And I think that this isn't implemented yet, but I think, but it will be over time, and I think will be an important part of the XX network ecosystem, which is the ability to enable your device to send messages to other users that using some probabilistic algorithms, which look like real communications and look like your communications. And the idea here is that by having a lot of data, which is indistinguishable due to end-to-end encryption, due to the mixing from other data, you make this further harder. Now, the question of is this perfect is an interesting one, and I think that this is an area of continual development, but CMIX really gives you a foothold to start working on it and to continually improve the privacy. And I think that's kind of what we're excited about. I think like any other area of technology, it's never one and done. But it really, I think, has a bright future. Ethan Connolly also asked some questions about praxis. So his first question was, how do we get around Shor's algorithm? Will, I think this is for you.
Sure. I'll preface this by saying that I am not a cryptographer, so I'm sure our cryptographer will cheer me apart for something I'm about to say, but I'm happy to answer it at the level that I'm familiar with. So there's Shor's algorithm is, it's a good question, and Shor's algorithm is particularly important or relevant to us because it drives a lot of the decision-making behind the protocols used in the Praxis network. Shor's algorithm basically breaks in sufficiently sized quantum computers. It'll break the large prime integer factorization problem, and also the discrete log problem. So a lot of the signature mechanisms and encryption mechanisms or protocols that we're familiar with, RSA, ECDSA, DSA, using Shor's algorithm in a sufficiently large quantum computer, these will all be broken nearly immediately once, once and if this quantum computer appears. The way that we've addressed Shor's algorithm is that we don't use either the integer factorization problem, or we don't rely on the integer factorization problem, or the discrete log problem. We use hash-based signatures, which hash functions are based on pseudorandomness, and so just by design, these signatures are fundamentally resistant to Shor's algorithm. One thing that is important to keep in mind is there are ways to actually weaken hash-based cryptography using quantum computers. This is what's known as Grover's algorithm. I mentioned this in the chat. And there's actually a third mechanism, which is not reliant on quantum computers, called the birthday paradox or the birthday problem. And that's particularly important because it can be combined with Grover's algorithm to weaken the strength of hash functions. What this means at a high level is that you need to choose hash functions that are sufficient length to keep your security. So when I say security, you might say a security level is 2 to the n, which is basically how long it takes to brute force attack in a particular encryption scheme or hash to try to find a collision. Technically, I think you would want something like 2 to the 100 to be fairly confident that something is secure against brute force attacks. By using something like Grover in combination with the birthday paradox, I think what you end up with is, according to literature, if I remember correctly, a 1/3 reduction, or a reduction to 1/3 of the classical security level. So if it was 2 to the 100, it would now be reduced down to 2 to the 33rd. Which is obviously a massive reduction. So all it means is that you need to basically increase the size of your hash function to accommodate that. So instead of 2 to the 100, you would use 2 to the 300, and that would give you a 2 to the 100 classical security level. So that's basically what we've done here to mitigate the attacks that are known against hash-based functions via quantum computers. We just make sure that we have hash outputs that are large enough to withstand even quantum computing protocols.
Just add on to that, this isn't just a theoretical thing. If for people who are node operators will know, about 2 months ago, I think, we pushed an update which increased the size of primes in the payload for CMIX to 4K primes, which means an individual message, because of how we combine them, is about 8,000 bits long. Part of the reason for this is to ensure that large enough hashes can be used by Praxis. So this isn't just a theoretical conversation. We're making real strides to making sure we can hit those security requirements. We have a question.
I'd add one more thing to that. This is obviously a topic we obsess over. We're also monitoring lattice-based crypto and all the latest stuff that's been coming out in terms of the post-quantum secure world, and the pre-computation method will work with that as well. So we're monitoring that situation closely. When it becomes an issue, we'll have an answer fairly quickly.
We have a question from Bulldog John, which is, can this be used to replace 2FA? I think Rick will take that.
I would consider 2FA completely complementary. You could implement a 2FA system over CMIX. You could similarly add 2FA to the existing library if you wanted to. It's not a replacement. It's not a it's an orthogonal tool and technique that you use in your toolkit based on what you're trying to build.
I want to point out that 2FA is a system designed under the assumption that things can be broken. So someone might have access to your email, but not your phone number. So someone has access to your phone number and email, but not your Google account. So no single system should replace 2FA because that breaks the fundamental assumption. Even the clients we've made, when you take them to the nth degree of security, it's still possible for someone to use human attacks to break them. So at the end of the day, it's fully complementary. You can use our system as a 2FA source, but I don't think you can replace it with it. There's another question, which I think is good for Will from Thinly Spread, asks, dApps, any plans for distributed exchanges?
It's a very good question. We've obviously thought about distributed, decentralized exchanges. I think what we would say is there is no plan in the moment for us to create a decentralized exchange, but we would absolutely like to provide you, the community, with the tools to create a decentralized exchange. And I think that's really kind of what our dApp strategy is moving forward in general. It's not necessarily to create all these dApps ourselves, but to enable you guys to create the dApps, because I think that's going to be important to maintaining the decentralization of the network, is that the community is involved in the development of all these products that are built on top of the network.
So we've got another question from Mark B. Will the permissioning server be abandoned eventually? And if so, how will this be implemented in a centralized way? The answer is yes. The permissioning server is an artifact of the BetaNet. It's an artifact of building two related but fundamentally separate projects which are to be joined, which is Elixir and Praxis. And I can't stress strongly enough, the permissioning server is not the final architecture of the network. It will be fully decentralized. We could talk for an hour about the problems of having a permissioning server in a network. It's an artifact of engineering challenges, not of our theoretical goals. As to how this will be implemented in a centralized way, this is a topic of conversation which is very common. I've had hours of conversations with Will, with David, with members of Will's teams, with Rick. We're starting to converge on solutions where we lean into as much asynchrony between Elixir and Praxis as possible. I don't have much more to say other than that. But the mechanisms are basically to have Praxis determine what teams will be formed, and then once they're completed, teams will report back to Praxis their results. I don't want to stress again, permissioning server is an engineering artifact. It is not a design goal, and it will not persist into mainnet, at least not for long. Quantum XX Network asked, have you thought of a plan in the coming days to introduce these wonderful works to the world? Hoping Will can get us some questions.
Yeah, so I think there's two things to say here. Yes, we will be rolling out some more information, particularly through partner blog posts, or blog posts in conjunction with the partners who are helping us build some of these dApps, as well as putting some interesting stuff on our website. I think we'd also like to encourage the community to, share in how they'd like to see this stuff rolled out, how they'd like to see it, what type of information they'd like to see. I would drive people to the Discord channel, and I don't know, do we have a dApp channel in the Discord channel?
Not yet. We can make one.
Yeah, so I think that's what we'll do. We'll create a dApp channel in the Discord channel and encourage you guys to start, communicating with us what you'd like to see roll out, and give us some ideas. Unfortunately, we are kind of operating at 110% capacity on all fronts at the moment, given trying to get this project out and prepared for mainnet. So we haven't come up with some genius marketing schemes for putting all this stuff out there. I think what we'd like to do is have you guys help us out with that. And so yeah, go to the Discord. We'll create that dApp channel, and like I said, we'll have some blog posts and website content coming out soon as well.
So we have a few questions asked as we're going. I think we'll take it in a more ad hoc manner. We had a question from Charles L. Perkins. How would someone integrate / load XX Messenger identities from all the unsaved contact universes? So one solution that we currently have is the user discover, we've mentioned, and we mentioned its flaws. Things like phone number and email, which are already distributed systems, I don't know off the top of my head another solution, but things like Facebook or Google or Instant Messengers, I think there are options where if we could work with those platforms themselves, they could provide signatures saying, here is a fingerprint of an identity. Google is assuring that there's a relationship here. So there are mechanisms where you still have to trust those entities, but you don't add another entity where you reveal it that may be possible, assuming those groups want to work with us. I'm not going to say that it's impossible to do integrations of these things without their help beyond what we've done to user discovery, but it certainly isn't easy. I don't know if anyone else on our team has any other ideas.
Yeah,
to add, just, sorry. Each of these is sort of making it weaker. It's a bit like building, a really huge wall that's very thick. It's 4 feet of brick, and then you add a bunch of doors. So, as from a user point of view, if it was my account, I might not necessarily tie everything to my XX Messenger account. I might not integrate it with Facebook, IM, Instagram, everything across the board, because each of those it's a sort of adding a door to that big wall. So part of how we've approached this is to make it really easy to share. So Rick mentioned QR codes, and we're looking at NFC for the future, make it easier for users to share and sort of control who they're sharing with their XX Messenger. So send it as a message on Facebook or send it on Instagram, rather than sort of integrating everything at once and undercutting some of the privacy by doing that. So it's up to you as a user. Yes, there are a lot of functionalities you will be able to use, but also I would say maybe use those judiciously and decide how you want to share your info rather than just putting everything together. Because that is kind of, Facebook right now, for example, all of your information is there, and that is the problem. So
I think I just want to add to Kate's point, which is I think what we're doing that's fundamentally different from everywhere else is we're going to give you that option to turn off the XYZ has joined network message that everybody else has, right? So that's a very key difference. If you want it, you can turn yourself on, but I personally don't want that. Don't want other people knowing that I've joined some network. In most cases, just because they're on my contact list or they happen to have me on their contact list, and I'm sure a large number of people feel that way too.
Yeah, I actually was thinking of that example when Ben was discussing what is metadata earlier. Metadata is, because it's conceptual and people don't necessarily see it, it can be hard for people to understand. But I had that experience earlier this year when there were a lot of protests in the United States and globally. I started getting messages from Signal saying so-and-so has joined Signal. And I got about 10 in one day, and putting, that information together with global events is hugely revealing of data. So that's an example of sort of metadata at work and what you can reveal from something that's, theoretically very small, just you have their phone number, they've joined this app, but when put together with everything else can be very revealing.
So we have a question from, and I'm sorry, I'm going to butcher your name. I apologize. Vyacheslav Vornochuk. I'm very sorry. Will it be possible to build own clients for XX Messenger, e.g. web? Will file transfer be possible by protocol or just relatively small messages? So this is a few questions, and we'll take them one at a time. It certainly will be possible. Web is an interesting problem. We've not tackled it. I expect it will be possible to compile the client to something like WebAssembly. How you transfer the client files is different. Our model is not a centralized server, so you've got this session file which defines your identity, and you have to transfer that file. It doesn't go over the internet for you. So how that transfers for browsers is an interesting question, and how we compile it for them is an interesting question. That's not one we've tackled, but I have a hard time believing it would be possible. For file transfer, you could certainly transfer files. It would be slow. You know, when you start looking at privacy-preserving technologies, they kind of break down into different categories. You have ones like we have that do delivery, where you're not just anonymizing a file, but you're anonymizing it to someone. And that's a little bit harder, and it's slower than just bulk anonymization. You put a file up there, no one knows what it is. And I think the long-term strategy will be that a second system which allows you just to anonymize a file, know where the anonymized file is, and then use something like CMix to say, hey, there's this file, there's this stream out there, here's the anonymous place it happened to end up in. And stuff like CMix is the backbone of a private infrastructure, but it's not the sum total private infrastructure, the same way that TCP and UDP exist harmoniously on the internet.
This is like the SMS of, private messaging.
And so eventually, yes, I don't know that we can do that immediately. Certainly, I mean, kilobytes and megabyte files, certainly. When we start getting to gigabytes, that becomes a little bit more difficult, but not impossible. There's a question about VoteXX in the chat. I don't know if Rick or Will want to take that. I don't know if we're
sure.
Discussed.
Can you read it for me?
Yeah, VoteXX project. Will the user receive a receive/log vote message back? What will the voting system need to integrate for this?
So VoteXX uses the anonymous messaging in CMix to perform some of the operations that it does. The best way to think of how the voting process works in these types of vote, and there's videos and research papers where you can read all about this in detail. But the best way to think about it is we create this digital audit trail from think of it like a code number that paths through to a candidate ID, and you are voting for that code number, and that's what publicly gets posted. And then and all that information, all those, there's like, think millions or thousands of links between that code number and that candidate. And then after the election, we reveal all but one of those links. And we don't decide which link until after we publish results. So it's kind of this protocol of we post things, you do things, we post things, and then an audit that is very public and very hard to manipulate happens after the fact. And that's kind of the fundamental reason that the system works. I can, if that doesn't answer it, I can give more detail, but I don't want to spend 4 hours on this.
I think those are all the questions. If we missed any, please comment. I'm not trying to skip any. And I think that's pretty much it. I mean, this client is available hopefully next week, if not the week after. We'll have a network up for you guys to start testing it, and I think very soon this will be live on the network. We want people to build this. We want people to use it. We want to support the world. We think that this is something the world needs. So bye. Thank you for your time, and I hope to talk to everyone here soon.
All right.
Bye, guys.
Have a great day.
Thanks, everybody.